Up to now, you were often given a linear system and you were simply asked to solve this linear system. However, many linear systems you will encounter are the result of the analysis of a problem. In this video, we will investigate such a problem and see if we can come up with a linear system that needs to be solved. Consider this spring, which is hanging from the ceiling and has a block of wood attached to it. You may remember that this mass spring system satisfies Hooke's law. The force F needed to move the mass a distance u from its equilibrium position y is proportional with this distance u, or in the formula, F is equal to k times u, with k some positive constant. Using Hooke's law, you can show that the length L of the spring with the block attached to it satisfies the rule L is equal to A plus B times M in equilibrium. Here A and B are both positive constants and M is the mass attached to the spring. How can you find the value of the constants A and B? To find the values of A and B, we can do some experiments and record the results of each experiment. I did 5 experiments, in which I hung several different blocks of wood on the spring and waited some time. As soon as the block of wood stopped moving, I measured the length of the spring. For a mass of 10 grams, I measured the length of 6 centimeters. And for a mass of 30 grams, I measured the length of 6.4 centimeters. The other 3 blocks of wood gave me these lengths. I'm always fond of making pictures, because pictures tell more than tables. So I have drawn a scatter plot where each combination of M and L is a point in the graph. Note that I have put the mass M on the horizontal axis and the length L on the vertical axis. If we take a look at the formula for F, we see that all points should lie on one straight line. Obviously, that is not the case. And the reason is that my measurements of the lengths contain errors, which measurements often do. Now we have a formula, a table and a scatter plot relating the length L and the mass M. We could also rewrite our table to a set of equations, because each combination of a mass M and a length L should satisfy the formula. For example, the first measurement results in the equation 6 equals A plus 10 times B. The other measurements give these equations. We can rewrite these equations by putting the unknowns A and B on the left and all constants on the right hand side. This gives the following equations. But this is exactly a linear system in A and B. We have done 5 experiments and these resulted in a nice graph and a linear system. Because we can see from the graph that there is no way a straight line will go through all points, my linear system is inconsistent, so it will not have a solution for A and B. As we really do want to have a solution, we thus look for the best possible straight line through the 5 points, or in other words, find the best possible solution of the linear system. We do, however, need to define what the best possible means before we can do this. You will learn how to do this in class, and it turns out that this is the line corresponding to the best possible solution for our problem. For now, you should have come to the understanding that real-life problems can lead to inconsistent linear systems, which we still want to solve or find the best possible solution to.